Hi, my name is Jason Liu, and in today's lesson I will be teaching you how to solve number 3 on page 290 of the McGraw-Hill Ryerson Grade 12 Calculus and Vectors textbook. The question states, as radon decays, polonium is produced. The mass of polonium MPO in milligrams as a function of time is given by the function MPO to the t is equal to MO bracket 1 minus a half to the power of t over 3.8, close bracket. MO is the initial mass of radon, and T is time in days. Let's start by gathering the data provided in the question. We know the original function for the decay of radon and production of polonium. MPO is the mass of polonium, T is time in days, and MO is the initial mass of radon, which is provided and is 100 milligrams. So we plug in the 100 milligrams as MO into our equation and receive our final decay equation. Now we can start part 1 of A, which asks, how much polonium is there initially? The key word is initial, which implies that the time is 0 days. Henceforth, T is equal to 0. We can now plug in 0 as our T into our equation. We must follow the rules of BEDMAS and solve the exponent in the brackets first. So we plug 1/2 to the power of 0 over 3.8 into our calculator, and we should get an answer of 1. So our new equation is MPO to the 0 is equal to 100 bracket 1 minus 1 close bracket. Once again, we must solve what is in the brackets first and plug in 1 minus 1 into our calculators. This will give you an answer of 0. Our equation is now 100 times 0, and the final step is to plug in 100 times 0 into our calculator, which will be 0. Therefore, we can assume that initially there is 0 milligrams of polonium, and this makes sense because the radon hasn't decayed at all, so it cannot produce any polonium. Part 2 of A asks us how much polonium is there after 1 day. Just like in question 1, they provide us with the time, which is 1 day. We can plug in 1 as our T into our equation. We follow the rules of BEDMAS once again and solve for the exponent in the brackets first. We plug in 1/2 to the power of 1 over 3.8 into our calculator and get a rounded answer of 0.8333. Our new equation is now MPO to the 1 equals 100 times bracket 1 minus 0.8333 close bracket. We solve the brackets first and plug in 1 minus 0.8333 into our calculator and get an approximate answer of 0.1667. Our equation is now equal to 100 times 0.1667, and our final step, you plug those numbers in and receive a rounded answer of 16.67. Therefore, we can assume that after 1 day, there was about 16.67 milligrams of polonium produced. The final part of our question, which is part B, asks us to find the first derivative of the function and explain what it means. We're provided with the equation, and we're tasked with finding MPO prime. The first step is to eliminate the brackets by multiplying everything inside the brackets by the number outside the brackets, which happens to be 100. So 100 times 1 becomes 100. But when you are multiplying 100 by the half, you leave the 100 just outside the brackets around a half, due to the exponent with the unknown that is applied to the half. Now we can start applying the derivative rules. We'll start with the easiest number, which is 100. The derivative of any constant is automatically 0. So our new equation is now negative 100 times 1/2 to the power of t over 3.8. For this next step, we must recall that if an equation is something like y is equal to a number to the power of a function, that to solve for y prime, you copy the whole equation, ln the base, and times it by the derivative of the function in the exponent. So we will apply this rule to our own equation by copying the original, lnning 1/2, which is the base, and timesing it by the derivative of t over 3.8, which is equal to 1 over 3.8. The final step is to fully simplify by multiplying negative 100 by 1 over 3.8, which is equal to negative 100 over 3.8. Therefore, the first derivative of this equation is MPO prime of t is equal to negative 100 over 3.8 times 1/2 to the power of t over 3.8 times ln 1/2. To answer the second part of the question, which asks what this equation means, we can say that the first derivative of the equation represents the rate of change of the amount of polonium in milligrams per day. Now for some potential real-life applications of derivatives. These can be found in the fields of biology, physics, economics, and many more. For biology, derivatives can help determine the rate of change of the population of a certain species. For example, if a species is rapidly populating, they can determine how much is being produced and how much they must kill to prevent overpopulation, or in reverse, and calculate the limit of how much a certain species can be hunted before there are so few that it cannot repopulate. In the aspects of physics, derivatives can aid by helping one find the velocity or the acceleration of an object. For example, if two cars are going at the same speed and collide and create a given amount of force, one can use derivatives to solve for the velocity of both cars. And finally, for economics, derivatives can be used to optimize prices, thus improving sales and productivity. If you know the results of price changes to your products will have on the amount of consumers and sales, you can use derivatives to solve the optimal value to sell your product at to produce maximum revenue. Thank you for watching. See you next time.